the multivariable Newton-Raphson. Okay. So in this section, we study Newton-Raphson for solving a system of nonlinear equations. Therefore, we will have so the variable x in this case is a vector. Okay. So we here the system of nonlinear equations is defined by the equation fx equals 0, where f is a vector, x is a vector. Okay, so f is a vector of f1, f2 up to fn, and x is a vector of n variables, x1, x2 up to xn, right? So here we have the we have n unknown and n equations. Okay. So for each fi, for each I, fi is a real value function of n variables. Okay. And here we assume that fi is continuous. So f is a vector of continuous function. Here we, okay. You will notice that all the properties we derive in this course, many of them require the continuity property. So here we assume, as before, we assume that xk is xk is a current point or a current iterate. Then we wish to develop okay, a method to compute the next point, xk plus 1, which is defined as xk plus s. S is a correction vector. You see that this is the form of this is what we call the update equation. Okay. So once we, okay, given xk, we compute s. And okay, and then we obtain xk plus 1. This is how we obtain the next iterate, xk plus 1. Okay, now here we okay, this is a vector form, so we apply the Taylor series to each equation. Okay, to each equation. Then you see that fx x1 of xk plus s is approximately equal to f1 xk plus the dot product between the partial the gradient vector, the partial f1 by partial x is actually the gradient vector. Am I right? If you look at the Taylor series expansion, fx plus s is the fx, right? Plus the that fx transpose the s, right? Plus 1/2 S transpose the Hessian matrix S plus higher order term. Okay, the higher order term. This is the Taylor expansion, right? So the F, therefore the F I x k plus S is the Fi of x k plus the gradient of Fi x transpose the S plus something higher order term. Okay, so let me come back to the slide. Yes, then okay, so we apply that to each Fi, I from 1 to n, and then you see that what we have on the right hand side is the gradient of Fi transpose the vector S, right? So we write this again in the vector matrix notation. So what we obtain is that Fxk plus S is approximately equal to Fxk plus the Jacobian matrix J of xk multiplied with a vector S, right? So from equation 3 point, so from 3.16, then we have 3.17, where this is the in equation 3.18 we have we have how the Jacobian matrix is defined. Okay. So then we assume further that xk plus 1 is close enough to the root fx star so that fxk plus 1 is approximately equal to 0. So from this, then we obtain Newton iteration, right? Because f xk plus 1 approximately equal to f 1 is approximately equal to fx fxk, right? Plus the j xk transpose multiplied with s, right? And this is approximately equal to 0. You see, this is just this is when we do this, this is not exactly equation. It's an approximation. But from this approximation, we form the Newton equation. But when you do math, this is some in this you see that when this is not exactly equal to 0. Okay, this is just how we show you. I show you how the iteration is developed. But then in the analysis, equation is equation. Okay. When you write something as an equation, the left-hand side must be exactly equal to the right-hand side, not by approximation, not only approximation. Okay. Yeah. Okay. Then when then this is what we have. This is the form of Newton equation. Newton-Raphson in the multivariable form. Now you see that, from this, you will see that the S is a form of the vector S is the J X K S transpose S. This is equal to, from this, right? We form an equation to find the vector S. You see that the S satisfy the Jacobian at the point xk transpose multiplied with S equals minus fxk. So that this is equivalent to S is can be written as the minus the inverse of the Jacobian matrix. Okay, multiply with the fxk. Okay. But now you see that but I prefer writing the Newton-Raphson as the equation 3.19. I prefer this. Okay, I prefer this form to the form in which you write the inverse. On a moment, sorry. This is the Jacobian transpose. Right? Sorry. No, this is no transpose. Yeah, I think in this definition, this is not transpose. It's sorry for the mistake. Okay. But then this is the inverse. Minus J inverse fxk. Okay. So, and can you guess why I prefer this? Some people write fxk, k plus 1 equal xk, okay, minus j of xk inverse fxk, right? So the two equations are equivalent, right? But I prefer 3.19. Can you guess why? Emmanuel?
Then I think 3.19 provides a closer approximation to the global minimum.
No, they are equivalent. They are equivalent. When you read, can you guess?
How?
Can you guess why I prefer equation 3.19? Now, okay, if you don't know, then I ask you further. If you implement this equation, will you compute invert? Will you compute the inverse matrix? Yeah, we have inverse matrix, right? Axk plus 1 equals xk minus the j xk inverse multiplied with fxk. Aisha?
Yes, Professor, we have to take inverse of matrix.
Yes, so
I think
normally
3.19 is simple than the
that's not the no, that's not the point. The point is when you write equation, normally when people write equation, this equation, okay? This equation, they will compute the inverse matrix, right? I believe that most people do. If you are not a professional numerical analyst, you see that when you compute the inverse, the if you remember when we solved the in chapter 2 in the review of linear equation, in solving a system of linear equation, this is a system of linear equation, right? So when we solve this linear equation, we apply the Gaussian elimination or LU factorization, and the flops we need is in the order of, I think, n cubed over 3. Well, I think no. I think we need I think a 2 over 3 n cubed flops, right? When we solve this, but then if you compute the inverse matrix, then the job is, I think, is more than that. It should be 3 times as much as the flops, the number of flops we spent in solving a linear equations. So this is why, okay. And so 3.19 is the form in which we use in real computation. Now you see that normally okay, as a professional numerical analyst, we do not compute. Okay, we sometimes we choose, well, the form. I mean, the form that we used in real computation may not be the same as the form that we write down the equation. That is, this equation, okay, is implemented by 3.19. We does not implement it as it's written. Okay, so we try to avoid inverting the matrix, because I think the number of flops in inverting a matrix is, I think, 3 times more than the work we solve the linear equations. Okay, and this is the reason why. Okay, and okay. Then in practice, okay, you see that a Newton-Raphson required the derivative, right? The derivative is embedded in the Jacobian matrix, is in the Jacobian matrix. Now, as I said before, okay, in practice, we do not have analytical expression of the function f, and therefore it's not convenient to have to use analytical expression of the partial derivative of the vector x of the vector f, because in the real situation we may know the function as, okay, we may know f as a program, as a function. For example, okay, if we given x, we have fx. We know this as a black box. We don't have, it's difficult to find analytical expression of the partial derivative in practice, in many practical applications. So then in that case, okay, we, the partial derivative, partial fi by partial xj, is approximated by finite difference. This is a kind of approximation. Okay, I just show you that. Okay, the details is as well in the 507, in EE 507. Okay, now we look at this example. This example to illustrate how can we apply Newton-Raphson to solve a system of nonlinear equation. Okay, this is the f1 of x is equal x1 x2 minus x2 cube minus 1. Okay, whereas f2x is equal x1 square x2 plus x2 minus 5. Okay, to solve this, then we first form the Jacobian matrix. Okay, and this is the Jacobian matrix we have. So we compute all the 4 partial derivatives. Partial f1 by x1, partial f1 by x2, partial f2 by x1 and partial f2 by x2. Okay, we compute all four derivatives to form the Jacobian matrix. After that, we choose an initial guess, right? An initial condition, which an initial point x0 is chosen as 2, 3, right? So here we have fx0 and the Jacobian of x0. Okay, then we perform the Newton iteration, and you say that, okay, the first iteration, the second iteration, up to you say that eventually, here in the slide, you can see the convergence from the two norm, okay, from the norm of fxk plus 1. This is the two norm. Actually, you can use a two norm or, well, okay, or infinity norm or one norm. Anything will do here. So you see that you see that when the iterate xk is near, starting maybe from here, when it's near the solution, which is 2 and 1, then it converges very fast. It converges very fast. When you look at the now, don't forget, when you look at the definition of quadratic, again, in this case, but we don't give you a proof. In this case, a Newton-Raphson for multivariable, for multivariable case, also converges with a quadratic rate of convergence. You see that when this one, then that means the ek plus 1 is less than or equal something with the ek squared. Okay, suppose the norm of E, you can see that when ek is, let's say, less than 1, you see that when the norm of ek is less than 1, right? So ek squared is much less than 1. For example, if ek is, the norm of ek is 0.1, then the square of the norm of ek squared is equal to, for example, is 0.1, then is, sorry, if the norm of ek is 0.1, then the norm of ek squared is what? Is 10 to the power of minus 2, right? So that means the error in the next iterate, k plus 1, is less than the rate constant multiplied with 0.01, right? So it's getting much less. Then if we perform the next iteration again, it obeys this rule, then it converges very fast. And now you can see that it's the quadratic rate of quadratic conversion is very fast. And it's shown in this example. Now you see that the norm of the, you can see from the norm of fxk plus 1, it reduces very fast to 0, okay, as you can see here. Okay, so this is the end of the lecture on the multivariable case of Newton-Raphson's.